Aloha, Hana. Today I'm going to go over the regression portion of the lecture. A regression is the way that we look at inputs and we measure what they are outputs. And in a lot of the literature that you see about regression analysis, it will have something like this, where y equals x times beta plus e, a bunch of Greek letters. But really what this means is you have your dependent variable, your response variable, and that's a function of your independent variables times the coefficient, and then there's some error term. And for this class, you'll notice that for the y's, there's only one. You can actually have a lot more than just one. You can have more output variables. Uh, and then we'll first of all, we'll talk about simple regression, and we'll talk about multiple regression. And there's a lot of different names in here that you can have for the X and the Y variables that you'll see and other things that you will come across. There are, oh, before I do that, let's look at some of the graphs that we, for the correlation graphs. If I go over to the car data, first of all, I'm going to, let's see, we have the data where we look at, let's see, this one, we're looking at the price and mileage of the Malibu. And we computed the correlation coefficient. That's the Correl function, the correlation coefficient, which is CORREL. Then you have the two things. We drew a graph on it. The simplest way to do a regression is actually to add a trend line. I'm going to right click, add trend line. This will give me a line. And then down here, display equation on the chart, and I'll give it the R squared. If you don't like if you don't like the numbers, you can actually come in here and change the numbers or whatever. Oh, there we go. It's a little better, I guess. And this tells us some value. You'll notice when you draw a regression, there is a line, the trend line right here, this line that goes through all of the points. That the idea here is that this line will take the differences between the observations and the line itself and try to minimize the distance on here. If you just do basic algebra or actually arithmetic, instead of when you kept calculating the difference between these two, I mean, you could get the same difference by drawing a line like this and subtracting this because those differences will offset by this. To ensure that doesn't happen, usually we use something called ordinary least squares. And that's a big mouthful, but really what that means is you take this difference right here and you square it. You take that difference and you square it. That difference you square it. And then you minimize the differences between each of those. And the difference between the observation and the fitted line is called the residual or the error term. So we're minimizing the error terms. Because those values are squared, values that are way off, like for example, this one right here, this distance is going to be a lot further than say this distance right here. There's a much bigger penalty for that because it's squared. There's so you take all those, you minimize, and that gives you a line through the data points. And then when we tell it to, let's see, format trend line, we can tell it what kind of a line we want. The default is linear. You can make it exponential, logarithmic, polynomial. When you make it polynomial, you can say what order, that changes. If you want to change the structure of that power, linear is the most easy one to think about. Uh, when you're doing a regression, when you're doing a correlation, it doesn't matter what you have for your X or your Y variable. When you start to do things like a correlation or a regression, which is the X and the Y axis matter because you're using the X variable to explain what's happening on the Y. And so, I mean, this one's a little bit backwards in the sense that we're looking at how many dollars explains the number of mileage. If you're doing a regression, you probably want to do something maybe the other direction. So here, let's see. I'm going to add that a little bit. Let's see, insert. I'll just throw this one up here for now. If I were to, well, we want to, okay, so now we have this as a function of the mileage equals the price that we sell it for. We add the trend line. Trend line's in there, display equation on the chart. Clean this up just a little bit. Yeah. Okay, so now we have this. What this is saying is for every mile that we drive, we lose 13 cents. That's where the negative 13 times X is equal to. So if you're selling a Malibu, it's Malibu with 0 miles on it, it's going to be $19,700. And then for every mile you drive, you lose 13 cents. And so if you have, for example, let's say 100, or let's do 25,000 miles. We'll put the same equation right here. I'm just going to I'm just going to copy this. Makes it easier. Right here, instead of the X, I'm going to do times that value. And so let's make it dollars currency. So if you have a 25,000, this one's supposed to be a number. 25,000 miles on your Chevy Malibu, you can anticipate that you could hold the all else constant, set it as paribus, you could sell it for $16,377.50. If you increase the mileage, if you have 100,000 mileage car, you're looking at just over 6,000. That's how the power of doing a regression is that allows you to do some forecast. But there's a really simple way to add the regression. We can do the same thing with these other things. Like for example, we have bed sheet deaths and cheese consumed. So we're explaining the amount of cheese consumed based off of the bed sheet deaths. We do the same thing. We add a trend line and make it display the equation on the chart. If really we want to predict the number of deaths caused by bed sheets, we want to have that on the y-axis. In that case, you would swap the x and the y variable. Actually, I'll just do this. We could B A. Okay, there we go. Number of bed sheet deaths caused by cheese consumed, whatever units those are. And so as you eat more cheese, for every 1 unit of cheese consumed, there's 113 bed sheet deaths that occur, at least according to this model. That's it's a spurious correlation, but that's how you possibly could interpret that if there's some sort of relationship there. If we go to the Warner data, here's U.S. gross sales versus worldwide gross sales. Add trend line. You could add trend line. We can. Okay, so I forgot. I don't know which one is which. And so as you increase more domestic sales, you'll have more international sales. That's what that's saying. And we can do the same thing with each of these when you're comparing rating. This equation doesn't look very good. There's not a fairly weak correlation. But you could add a trend line and display the equation on the chart. That number is not very good. It's hard to interpret. I'm going to put this into a number. Okay. And so now we've got an equation that you can use some sort of a prediction based if you have faith on that model. So that's one way to do a regression. Let me go to our slides. There's a few things that are I think that are important to understand. R squared tells us how close the data are fitted to the regression line. It's a measurement that takes into consideration the residual between the point and the fitted line. And the closer to one, if you have a perfectly fitted line, you'll have an R-squared value of 1. If nothing at all works there, you'll have a value of 0. And it's hopefully you want something with at least a 50 with at least a 0.5 or 50% R-squared. Um, Ideally, you'd want something higher than that, but at least that's a really loose word. It's not really completely appropriate to compare R-squared using that for model selection because there's some complicated ways of how the number is derived. But you do want the model to fit something along with what the data set is. The residual is the difference between the observation and the fitted line. When you run a regression, you'll get an F statistic, and you use that to measure if the model's okay. You want it to be the significance to be 5% or less. And we'll look at some p-values from the student test or the TEAS test. And for each of the variables, those you also want to be less than 5%. Let me go to this data and we can look at it and I'll show you what I mean. Go to this car data. And so I'll run a regression. If you don't already have it on your computer, I'm going to click on, let's see, data. And oh, it's not there. Sometimes mine just goes away. So click on file, click on options, and then I want to go to add-ins, Excel add-ins, and then, well, that says it's there. I'm going to unselect it, and I'll come back and do it again and add it again. That's what I need to do in order to get it back in. I've never had this problem before my Excel 365. Let's see it. But I found that this works. Get it back in. So I'm going to click on that. And it should be under. Okay, and so I'm going to date. So I should have somewhere over here where I can look at data analysis. Okay, so you want to announce that. Okay, now that I did that added thing, the data analysis shows up. I'm going to click on that, and I want to, which is the data analysis, and we'll come over here, and I will click on regression. Okay, the Y range. Now I'm going to include the labels. I want to look at the normal probability plots because that shows me if my data is normal or not. Under the Y range, that's the output that I want. I want to predict what the price is. I'm going to select the price and then the X range, I'll pick mileage. So in my case, it's R1 to R61. And I'm going to, you can put it in a new workbook, a new worksheet, or you can tell it what range you want, either one. I'm going to put this one over here to the right. I'll click on that cell right there. I click OK. Now I've got this normal probability plot. Okay. So what I'm looking at, there's an R squared 78%, which is pretty good. Now, is the model going to be okay? For that one, I want to look at the F statistic. To use that, I'll look at the significance of it. That's a really small number. 7.73 times 10 to the negative 21. That's a lot lower than 5%. And so that means it's a good model. Next, I want to look at the coefficient itself. I have the mileage. So what I'm looking at, because I left the label in there, it makes it easy. The coefficient is negative 0.3308. I mean, for every mile that I drive, I'm losing 13 cents of value in that melody. The student test or t-test is important. For this one, we want to look at the p-value as long as it's 5% or less, and then we know that we can trust that coefficient. Also, that's really good. That's a strong coefficient. And so with this, we're good on this. Great. So we have our, we can make predictions. I think I looked at before, we use the regression from the graph. The equation on here, let's see, 25,000. I mean, I could use this equation down here. It's the same thing. So if I have 25, I'm gonna copy these values, and I've got the formats. So I can put those like that. This equals the intercept plus the mileage times, that, then we get that same value that we have up there, 16,377.98, 100,000 miles. Let's see. We choose these in here. So 100,000 mile car is going to, you could sell for 6,400, which is the same values that we had before. We can do the same thing over here. I'm going to throw this over here. So we're looking at the number of deaths. That's what we want. Data analysis, we'll run a regression. On the labels, we're going to have the number of deaths, which is a function of cheese consumed. And this one will output it right there. And so we have, if we look at the R squared on this, it's 89%, which is really good, a strong model. If we look at the F test, you'll notice that this value, the significance of F is less than 5%. It's just wrong model. We look at the coefficient, we just have one on here. The cheese consumed. So for every 1 unit of cheese, it's related to 113 and an 8 deaths that occur. We do the t-stat, the p-value of that is a lot lower than 5%. So that's pretty good. That's a pretty strong model. It might be a coincidence, but there is a strong correlation between the two. We could do the same thing with these other, when we run the data, run a regression. I'll just do one. The budget versus total sales. And one thing you want to make sure is that you have all these data points. If you have any blanks on there, you want to clean that up before. So insert, let's see, data analysis, regression. We want to measure sales as a function of production budget. We have labels. We want this to be output. Okay, we've got an R squared of 0.46. It's not a very strong model. The model is significant. Great. So I think we can sort of proceed on that. It's kind of hold your nose. If we look at the t-stat, so for every production budget dollar, according to this model, it adds $3 of revenue. That's a pretty good return on investment. But with R squared of 0.46, you're only explaining that about half the time. That means there's a lot of other structure, there's a lot of other things that would explain how you have the worldwide revenue for sales. Okay, there's our single regression examples that we have. And we'll go back to here. You generate a scatter plot, calculate correlation, build prediction equation, validated assumptions. There's a few assumptions you want to make. You want to assume that residuals are normally distributed. If they're not, if you don't have a constant variance, if residuals are dependent on each other, that means there's some other structure that's not being accounted for within your model. And there's a bunch of treatments you can do. A really powerful tool, especially when you're doing multivariate regression or regression with 2 or more X's, is something called dummy variables. I've never liked the name because they're actually pretty smart how they work. And in this one, you create a reference value. It's hard to put a number, a value for yes or no, but actually what you can do is you create these what are called dummy variables. when you run your regression, you'll get a coefficient based off of the presence or absence of something. And so, like for example, if you have yes or no, or male or female, or whatever, what you'll set one as a value of 0, the other is a value of yes. So the absence of the yes is going to be a no. And then that way you can run a regression. You can fit a line through this. If you have multiple categories, like for example, banana, guava, lilikoi, these are maybe what I should do for these. Let's see, I think there's a text on it, but so this one is guava, and this one is really cool. If you don't have guava or lilikoi, like if both of these are 0, that means it's a banana. By putting a value of 1 under the guava variable, that means the fruit you're looking at is guava. So you're looking at this. What this will tell you is the added effect of having a guava. The same thing with lilikoi. The added effect of having lilikoi from your base banana is going to be something. And uh, if both of these are positive values, if guava adds more value than what a banana would have, or lilikoi more value than a banana, if you start switching things around, really you'll end up with the end. It'll be if it's based if lilikoi is the most adds the greatest value, then your guava and banana will be negative if it's based lilikoi. But really, it'll come out in the wash. It's a zero sum game. What you take away from one, you add to the other. And let me show you an example of a model that has dummy variables and how we can apply that and how we can interpret that. And I think this is where it gets really cool. This is where it gets really useful. And one of the reasons why something like this might be important. I'm going to go to the car data. If we look at the data, we've got these out of there. If we look at this data, we have a bunch of variables on here. So we have the price, and then we have this how many liters the displacement the engine has, how many cylinders, how many doors, and then what says cruise control, it's going to be either the value minimum 0. Okay, there's max is 1, some 605. So you have about 200 that don't have cruise control. A 1 means that you have cruise control. So we'll look at, by having this dummy variable, we'll have the effect of having cruise control. With sound, if there's some sort of premium sound system or whatever that is, this will tell us what the effect of having a sound system, is leather seating or not. Okay, so let's go ahead and start working on our regression. I'm going to pick the price of the car. And I'm looking at all of these cars. Actually, you know what? I'm going to add, let's see. I'm going to add a couple of variables in here. I'm going to add some more because we have, insert. So we have different types of makes of cars. The Buick, Cadillac, Chevrolet, Pontiac, Saab, and Saturn. And so let's say we do, for example, base Buick. And so I'm going to write Cadillac, Chevrolet, Pontiac, Saturn. And then I'll just write a couple of fancy formulas. Equals if this is equal to that, give it a value of 1, 0. And so it's a Buick, which is what our base is. So all of these should be 0. I'm going to anchor these real quick. That way I can copy this all the way through really fast. Okay, that's 0, like I would hope. And as I go through here, if it says Chevrolet, that means it's not a Cadillac It's not a Pontiac, Saab, or Saturn. It's a Chevrolet. And remember, we're base Buick, the one that you don't see. Great. Now they've got all this stuff in here. I can do my data analysis. I'll run my regression. All for the price. We're looking at this thing right here. We have labels selected for the X range. Let's go ahead and pick all of these. And then I'm just going to put in a new worksheet. I'll call this the full model, because that's what it is. Okay. And give this a moment. Oh, that's not super linear. We want something a little more, but I think a lot of that has to do with, let's take a look at this model. We have R squared of 88%. That's okay. It's pretty good. It's a really strong model, pretty close to zero. So that's a very significant model. When we start looking at these p-values, some of these aren't as good. Let's see. Equals if this is greater than 5%, give it a 1. Actually, intercept usually don't count. So we have 4 of these aren't very good. Like this one right here, or these 3. So that's a number of cylinders, cruise control, sound, leather. I mean, let's talk about what these, if these models were, if all these variables were good, let's talk about what that means. So the intercept really doesn't mean a whole lot. The number of liters, every liter you have in your engine adds an extra $4,700. Every cylinder is minus 215. These 2 variables are likely related to each other. So you want to get rid of one of them. So because to tell the story of what we're doing here. The doors, you lose 1,700. Why would you lose money for a door? Sports cars usually cost more, which is why that one would be probably negative. Adding cruise control is negative. It's not very significant. There's probably some interaction with cruise control and something else. But the way this model interprets is that having cruise control loses $500 of value for the car. The sound system, we lose $44. Having leather adds an extra $25. Each mile, you lose 18 cents. Now that's different from the 13 cents before. That's because this model is taking into account more than just the mileage. That's where this gets a little more important. If it's a Cadillac sells 16,000 more, and then a Buick, and Buick was our base. A Chevrolet sells about 2,200 less than a Buick. A Pontiac sells $1,700 less than a Buick. A Saab sells almost 15,000 more than a Buick. A Saturn sells 2,200 less than what a Buick is, based off of what the base is. Now, this is one model. If I wanted to compare my models with each other, I want to do something called the AIC. And in this one, I have it saved. And for an exam, I'll just give you this formula. You don't have to memorize it. But what you want to do is look for the lowest Akiaki information criterion. AIC stands for Akiaki information criterion. I'm just going to copy that right here. And I'll put it right here. If I click on this model, it does a bunch of fancy math based off the number of observations, degrees of freedom for the model, and with the SS from the residuals. And it gives us a value. What? So this model right here, the full model would be preferred if you're comparing that to using just the mileage. It is better until it would be preferred. You would want to select that over just mileage. And really what you probably want to do is look at these, think about what variables might interact with each other, because that interaction can throw your model off. Just get one that tells the story. Get one representative variable. So the number of liters of cylinders, those, I would get rid of cylinder or liter, one or the other, one that would make more sense. And you'll probably have, that might be not, well, let's see, yeah, let's do that. Copy. Okay, so I'm just going to make a model over here with the variables that I want. So let's see more. Okay, so the variables I want to consider. Okay, we have, I'll just do liter instead of cylinder. That might be good. We go to data regression. So we'll have, okay, that looks good. And then this one, we'll go P instead of Q. Almost full. And let's see what this gives us. The cruise control is not really that important. Sound, not as important. Weather. Those are three that I think, if I remember right, they gave us some problems last time. If I look at the full, yeah. And so really maybe I want to exclude those. Let's see, we have, this is the copy of this. I'm just going to get rid of these three. And then I'll run the regression again. And you kind of play, I think so. It is a little bit of an art to figure out what model you're going to have. And then you can do model comparison using AIC. So regression, that, and this one. Let's call this a partial model. Use a name that makes sense. And that gives us get significant. And these p-values all look really good. Great. I suspect this one might have probably one of the better AIC values. Let's see. So 13, 111, let's see, 6. So this partial model looks like it's better. Yeah. And so we'd want to, the partial model is probably the one that we would adopt. And what this tells us, if you have a car that is, let's do a prediction on here. Let's see. You'll take the intercept. If it's a 3-liter car, you have 2 doors. So you have 15,000 miles. And let's just say it's a Buick. So all of these are 0. You could do, let's do a sum product. So the coefficient times our X, and then go sum all of these. So if you're selling a Buick with a 3-liter engine, 2 doors, 15,000 miles, according to the model, the price that you would sell it for is $22,266.65. If you end up selling, if it's a Cadillac instead of a Buick, then you're looking at 30 with the other holding everything else constant. You're looking at $38,500 for what you'd sell it for. And that is, let's see, that's our let's see if I skipped anything on here. Okay. Well, lowest AIC t-test coefficients, F score, decent R squared. The Six Sigma Society, I think they want you to look at a decent R squared, but they have these other rules that they put into place that I haven't seen anywhere else, but I'm sure they're good. And then so we talked about predicting variables. So yeah, you use these coefficients to predict what you have. Anyways, I hope this was useful in understanding how to run a regression. Running regressions is an extremely powerful tool, and with it, you have the homework. You'll have the class quiz, which I turned to homework, and the homework includes a few other practice problems. I would highly encourage you to become familiar with this. This could be a very powerful tool that you could use to add a lot of value to understanding, analyzing, and being able to make predictions with using data within your organization. Send me an email, stop by during office hours if you have any questions about this. Thank you very much. Mahalo.